Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and in the next lecture of ECE3084, we'll take a look at filtering for power supplies. And for that, we're going to need something called Parseval's theorem. So let's talk about that theorem today. So I have two functions of time, f and g, and I'm going to integrate these functions over time. And what we'll see is that this is equal to 1 over 2 pi times another integral that looks basically the same, except this is going to be the integral of their Fourier transforms multiplied together with one little twist. We need to put a complex conjugate on g and a complex conjugate here on capital G. So on the left, this forms something called an inner product. So this would be like an inner product between f and g. And over here on the right, we would have an inner product between capital F and capital G, the functions in the Fourier domain. So this inner product business isn't something we've emphasized very heavily in this class, but it yields all sorts of cool mathematical structures. Now, we have a special case where f and g are the same function, and then we can write magnitude of f squared, integral over time dt, is equal to 1 over 2 pi integral of magnitude f squared in the Fourier domain, so that's our capital F d omega. Now, in order for this theorem to hold, both sides of the equality have to integrate to things that are well defined. For instance, if I were to write ft equals cosine t, well, what's on the left would integrate to something infinite. What would the thing on the right be? Well, the Fourier transform of a cosine is a couple of delta functions, and you would be taking these delta functions and you would be squaring them. And squaring a delta function doesn't give you anything meaningful. This is mathematical nonsense. So what's on the left needs to converge to something finite, and what's on the right needs to converge to something finite. Fortunately, there is a version of this theorem that applies to periodic signals. So if you want, you can integrate over any period of a periodic function where I have ft, and then I multiply that periodic function by another periodic function, g, with the same period, and we need to remember to put in the complex conjugate there. Oh, and we also need a 1 over t naught in front. Well, this is going to equal the sum of the associated Fourier series coefficients. So let's write the ones for f as ak, and let's write the ones for g as bk. And we do need to put a complex conjugate here. So this is now like an inner product over these Fourier series coefficients. And again, if we have the special case where f equals g, then we could write ft magnitude squared, integrate over any period for that. And over here on the right, we're now summing the magnitude squared of the Fourier series coefficients. The version down here is called Parseval's theorem. If I recall correctly, the version up here at the top is technically Plancherel's theorem, although engineers will tend to call it Parseval's theorem anyway. And I'm not sure if I'm saying Plancherel correct. If you know a more correct way to pronounce that, let me know in the comments below. This version on the bottom for periodic functions is what we'll look at in detail next time. As far as this lecture goes, I want to focus on doing some examples with the version up here. Okay, so let's do an example. Suppose it came to pass that you wanted to perform the following integral. Suppose you wanted to find the integral of sine 4t squared over t squared, t going from minus infinity to infinity. First of all, you should question your life choices in which you need to solve this integral. But secondly, if you tried to tackle this using your standard freshman calculus techniques, you would probably have a difficult time. So let's see if we can change this integral into something a little more amenable to the tools we currently have. Let's take the denominator here and multiply it by pi squared, and then I'll multiply by pi squared up here. So I'm not really changing this expression any, but now if I take a look at this, this looks a little something like sine 4t over pi t and whole thing squared. But notice that this is real valued, so it's the same thing as magnitude squared. So, according to this theorem up here, this is equal to 1/2 the integral going from minus infinity to infinity of the Fourier transform of this. And well, I know that the Fourier transform of this sinc function is just a boxcar function going from -4 to 4. Oh, and I forgot to put a pi here. Let me put a pi here. So let's see. So this is equal to 1 over 2 pi. And I have a rectangle that has length 8 and that has height 1. So that's 8. So this whole thing is just 4 over pi. There you go. Okay, that was fun. Let's do another example. Suppose I wanted to perform this integral. I have 10 over 9 plus smiley face squared d smiley face. Now, the first thing you should realize is that the professor is being tricky and trying to disguise the nature of the problem using the smiley face variable. If we were to compare this to the sort of things we see in our Fourier transform table, it looks kind of like Fourier transforms more than time functions. So let's start with this. Let's take the smiley face and replace it with an omega and see if we can massage this a little bit into looking something more like what we want. All right, so now what I'm going to do is I'm going to multiply by 2 pi in front and then divide by 2 pi. So I haven't really changed the expression. But now, if I look at this form here, it starts to look like what we have on the right. I have that 1 over 2 pi. Now what I'm going to do is I'm going to take the 10 and pull it out in front, multiply it by the 2 pi, so that will give me 20 pi. And now let me write this as an integral from minus infinity to infinity of something I can get by factoring this. So let me write 1 over 3 plus j omega times 1 over 3 minus j omega. So if I multiply this through, the 3's multiplied together, giving me a 9. The cross terms cancel. The j's multiplied together, giving me a minus that cancels with this minus. And then I have a d omega. Oh, and I also need to make sure that I remember to divide by 2 pi here in front. So what does this whole thing equal here? Well, I still have this 20 pi that's sitting here in front. But now I can use this theorem here and write this integral of the inverse Fourier transforms. So this 1 over 3 plus j omega, it has an inverse transform of e to the minus 3t ut. And so let me take the ut and incorporate that by changing the lower limit to 0. And then for this second factor here, well, it's a complex conjugate. If the complex conjugate is 3 minus j omega, then the original function, capital G, is 3 plus j omega. So I have another e to the minus 3t here. And technically speaking, I want a complex conjugate here, but taking a complex conjugate of something real just gives you the original thing back, so it doesn't really change anything. I also technically have a ut here, but we already dealt with that. So let's see, I have 20 pi times the integral between 0 and infinity of e to the minus 6t dt. Let's see, so I have 20 pi, and then I'll have e to the minus 6t over minus 6 evaluated at t equals 0 and t equal infinity. So for the t equal infinity, that goes to 0. When I evaluate it at t equals 0, e to the 0 is just 1. And let's see, it's the lower limit, so the minus goes away, and I wind up with 20 pi over 6, or let me write this as 10 pi over 3. And there you go. Okay, that's enough examples for now. Before we close out, I would like to actually prove this property. And in order to do that, let's recall the multiplication property of Fourier transforms. So if I were to take ft and gt and multiply those together and then take their Fourier transform, that corresponds to taking a convolution in the time domain, but we also need to divide by 1 over 2 pi. Now, something else I'm going to do is I'm going to take the complex conjugate of g over on the left here, and that corresponds to taking the complex conjugate of g on the right, but also a mirror flip. Let me take what's on the right and actually explicitly spell out the convolution. So I'm going to write this as 1 over 2 pi, and then we'll integrate from minus infinity to infinity of f of j. And let me put in a little zeta here. This is just so I have some variable of integration that's not an omega. And then I'll have g complex conjugate, j, and then normally it would be omega minus zeta, but because of this minus sign, I'll actually have zeta minus omega. And then by the fact that I put this equal sign here, you can probably predict what I'm going to do on the left is I'm going to explicitly write out this Fourier transform. So let's integrate ft g complex conjugate t from minus infinity to infinity, but we're also going to multiply it by e to the minus j omega t, and we're integrating over time. All right, so all we need to do now to prove the theorem is just let omega equal 0 on the left, so that this here goes to 1, and let omega equals 0 on the right. And there you go.